In this video, I want to go over all the concepts needed to master counting in the IB Math Analysis and Approaches track. A reason you may find counting hard is that it's a completely different mathematical system from arithmetic because down at its core, it relies on a structure called a Boolean algebra. This is essentially what propositional logic or zeroth order logic works on. And in this way, counting, or the academic discipline of combinatorics, is more closely related to how computers operate than everyday addition, subtraction, multiplication, and division. For brevity's sake, there are two principles of counting: multiplication and addition. Ironically, due to logic, multiplication is more fundamental than addition. That's the first thing we need to get started first. Multiplication is seen as analogous to looking at intersections between sets, a structure that is much more limiting in a way. Addition is analogous to the union of sets instead. And now here are the principles of counting for multiplication and addition respectively. First, we have the counting principle of multiplication, which basically says assuming you have countable independent events. So this notion on independent events is very important. That's a must. So assuming you have countable independent events, if there are A ways to do one action and B ways to do another action, then there are AB ways to perform both actions. And this can be generalized for any n countable events. So let's say we let E1, E2, ... En be events. Then we can simply find some fancy thing called the Cartesian product, which is basically just think of it as just multiplying all the events together, which will be written as like E1 as E2, ... En. This is equal to each of the individual number of items in these sets or events being counted together. And I just write for clarity that let S be a set. Then S here with the absolute bars here is called the cardinality of a set. Of set S, which counts the number of items in the set. Yes, and as I repeat again, finding the number of elements in this set just requires us to multiply all the items in the individual sets together. Now, events being independent mean they are not dependent, and so therefore do not follow the rules of, well, for the natural numbers at least, the natural number equivalent of what Bayes' rule is. And this principle aside, counting principle of multiplication, there is also the counting principle of addition. This says, assuming you have countable disjoint events, so we emphasize this word disjoint. I'll explain that in a moment. If there are P ways to do one action for one set A and Q ways to do another action for one set B, then there are P plus Q ways to perform both actions. Formally, we can write this in the following way. So, set A, P ways to act. Set B. Did I say Q or... Yes, I say Q. Okay, and capital P. Q ways to act. And a number of total ways to act in the union of these sets. Yeah, let's make the more... Okay, that's a bit too over-exaggerated, but now you could definitely get the idea. Equals the cardinality of A plus the cardinality of B, which is P plus Q, simply. And we can generalize this for n countable events again, which are disjoint. So E1, E2, En, same thing as before. And you just get, hang on, I need to figure out how to divide the room. Q, give me a second here, please. E1, union. Yeah, and that's just like all of the sets being added together. Now, disjoint events are simply events where the sets do not overlap each other or have no intersection. Their intersection is empty. And not just any intersection in general, any pairing you take of any of these events or sets has to be basically disjoint or empty as well. So we can write it as the following way. So to give one example, in like these abstract terms are here, like E1 and the intersection of E2, that has to be the empty set. Similarly, you could do the same thing with E2 and E3. That has to be the empty set as well. And then so therefore for any arbitrary indices I and j counting the sets, so let I, j be natural numbers, marking the sets, E of I intersection E of j always has to equal the empty set. So this is our disjoint criterion. And the best way you can understand from like set theory as to how these sets look disjoint is if you go and like picture them in the Venn diagram. Basically, the regions or areas of those circles will never overlap each other. Now, I would like to go over very informally partitions, and then the definition of a factorial to build up to the tools of permutations and combinations, a very useful tool used in counting. Partitions are intuitively the different ways we can split up a number into different components through addition. So let's take a look at a concrete example. In the case of, let's say we have the number 4 here. Let me define a partition function p of 2, 4 here. We can split up 4 into 0 plus 4, 4 plus 0, 3 plus 1, 1 plus 3, 2 plus 2. We do not just have to partition it into two summons. We can permit any number of numbers to be added together. So we could also have like 4 equals 1 plus 1 plus 1 as well. Here the 4 is split up into 3 parts. Where the structure of a Boolean algebra helps us is that the fundamental operations of addition and multiplication have reverse undo operations called inverses. So these inverses are respectively, you guessed it, subtraction and division. This allows us to sneakily add 0 and multiply by 1 anywhere we want into an equation and still preserve its equality. This is relevant to us in the following way. So consider the equation 4 equals 3 plus 1. Basically, I split up this number into 2 parts, right? So if it were this general to be like, say, like some expression or variable n, I can split it up into 2 variables, r1 and r2, that make up this guy. But because of subtraction, I can rewrite this 3 simply as 4 minus 1. And technically, this was a case of just adding 0 by itself, because you could just get like 4 equals 4 here, and I just arbitrarily added in -1 and +1 over here to the picture. -1 plus 1. And then we go in the opposite order, taking care to group in parentheses the 4 minus 1. Now, where is this important? Let's say we have like n items of whatever, like markers, for instance. I can like take r items out of those guys, and there will be a remainder of n minus r items left in the pile. So this is very helpful for us to distinguish 2 sets of objects that we're looking at. Yeah, so we can repeat the same game for any arbitrary finite partition. Say we have 26 sets, which correspond to the letters of the English alphabet. And let's let this item in the union of the sets, let S equal item in union of the sets. Or should I say the number of items there are in the union of these sets? I can simply write this as S equals P1 plus P2 plus ... ignore the stuff in between, P of 25 plus P of 26. And then we can generalize this for any finite number of n items in there as well. Now, each of these elements through subtraction can be expressed in terms of S and maybe just one add-in, but the way you do so will get more complicated as you increase the number of stuff you have to add and subtract in there. I would like to now introduce the necessary algebraic object of the factorial here. So assuming the well-ordering principle, WOP, yeah, which is that the natural numbers have a least element. The natural numbers have a least element, namely like 1. The factorial is defined as the product of consecutive natural numbers from 1 up to whatever number you specify. Mathematically, this would be written as the following. N factorial equals n times n minus 1 times n minus 2 times ... times 3 times 2 times 1. And we have to start with 1. We have to start with 1. That's where 1 begins in the naturals. 1 is the element of the naturals and is the smallest item. Remember as well that factorials are recursive. That means you can define them in terms of previous elements in the sequence. So another valid representation of n factorial is n factorial equals n times n minus 1 factorial. And this thing here, this guy here, I just took all the previous n minus 1 factors to the right of n and just grouped them up together. That's all it is here, and therefore I can refer to previous elements of the sequence. Which, if we set it n equals to 1, you get 1 factorial here equals 1 times 1 minus 1 factorial. You therefore get that 1 factorial is the same thing as 1 times 0 factorial. And 1 times itself is just 1 here. So 1 equals 0 factorial. Voila! That's random equation comes from that we use a lot by convention. Combinatorially, we can also define the factorial as a number of ways to rearrange n items. So this is important. This is an algebraic approach. This is now a combinatorial approach. The factorial from Combinatorics, number of ways to rearrange n items. Now we're going to put our informal knowledge of partitions into practice with the factorial to derive the permutation and eventually combination formula that you use in everyday high school algebra, or in this case in the IB, AAHO, and perhaps AASL analysis and approaches course as well. Okay, so once again, and here I'm going to actually draw a picture here. And draw a set and a subset inside, including that. Say we have like n items inside the set, and they could be dots or whatever have you. And then we want to pick like r items inside of it. So this is like r items now in the subset. To do so first, when selecting the objects, you must rearrange or permute the original n items you have there first. So by the combinatorial definition, that is simply going to be n factorial. You have to go and take all these dots here and move them around all over the place, essentially. But if you were to like take a subset, a certain selection outside of it with like r items, then in order to see how many stuff you have left, you have to go and divide by n minus r factorial items. Why? Well, you pick r items outside of the set. There are only now, just like by the partition thing, n minus r items left. Let me make this bigger. When you pick the thing out, and let me make this bigger as well. This is the key principal formula. So we start with n factorial. When you have n minus r items left, you gotta go and divide by the number of ways you're rearranging the remaining stuff that's left in there. So that gives us a factor of 1 over n minus r factorial here. And yeah, they must be discounted from overcounting. Remember, I mentioned about disjoint sets a while ago. One of the biggest problems that happens in like combinatorics is that we overcount things all the time. It is so easy. And so therefore, to remove the intersections and make our sets disjoint, you can always go and divide by the number of items you have from some set outside of there. So in this case, we're going to divide by n minus r factorial, and then get this. This allows us to count items while still, and here's the key important part, appreciating their distinct identity. And this, formally written as a two-variable function or sequence, in this following notation I'm going to use, P of n comma r, is the permutation formula. Therefore, in permutation land, everyone is special and no one ever gets left behind. However, if you just want to objectively treat the items you select as, say, wage slaves or proverbial cogs in the machine, then one can get what is called a combination merely by dividing further out the rearrangement of R items you already picked out. So all this stuff that we picked out here, it can be reassorted or rejumbled around by R factorial again, and then divided out by that to compensate for the overcounting. C of n comma r equals n factorial over n minus r factorial divided by r factorial now. And now I want you to take notice of a couple of interesting things when comparing these two formulas with each other. Do you notice anything at all? I'll give you a second to think about that while I go and rewrite and place them all together now. Yeah. Okay, so the thing I'd like you to notice is that the combination formula is simply the permutation formula scaled down by this factor of 1 over r factorial here. And for that reason in general, you will always have more permutations than combinations when looking at an object. Here, since you are only picking one item out of two sets, we model the algebra for this counting through binomials. Remember, bi means 2. But in general, as in the case of arbitrary partitions, we can split into 2, 3, 4, even more objects at a time for a set. So we can model counting trinomial, quadrinomial, pentanomial, and arbitrary multinomials in general. Though I say multinomial coefficients are outside the purview of the IBAAHO course. So I will ignore this now unless there is further interest. Now, I would like to go over the binomial theorem, though, because that is very essential to, in fact, it is identical to the numbers you get from the combinations formula here. But before we go to there, I would like to look at extreme cases of the permutation and combination formulas. It is very useful in combinatorics to consider the extreme cases to check that the formulas correspond with our common sense. For example, say we picked out n out of n items from a permutation. So let's take a look at here. We have P of n, comma n. This equals n factorial over n minus n factorial here, which is n factorial over 0 factorial. And we already proved that 0 factorial is 1, right? So I showed from the recursive definition. So n factorial over 1, we get n factorial, which corresponds with how we define the permutation combinatorially. We have n items here, we permute n of them, we get n factorial in general. Everyone's happy. Let's do P of n comma 0 now. N factorial over n minus 0 factorial. This is n factorial over n factorial. This equals 1. This makes sense because there is only one way to permute 0 items. You absolutely do nothing. So that makes sense if we're happy here as well. Let's do C of n comma 0 now. I'm going to do with comma 0 instead of select 0 items instead of select R items first. We get n factorial over n minus 0 factorial divided by 0 factorial. So this is n factorial over n factorial times 1. 0 factorial is 1. Again, we get the same thing. So for picking 0 items, we get the combinations and permutations are exactly the same thing. Once again, there's only one way to select, without caring about the identity of the objects we're counting, a combination of 0 out of n items. Now, let us take a look at C of n comma n. This is going to be n factorial over n minus n factorial over n factorial. And now let me go and highlight this thing in color here. for importance here. This might give us the answer of 1 in the end, which might seem a bit unintuitive at first, but remember, okay, so by the algebra we just get 1 here. But remember, by definition, the permutation goes and rearranges n items around. So we have like n factorial. However, permutations just in general always will overcount. So to compensate for the overcounting and to therefore make the guys you're looking at, Alice, Bob, and Carl, or whatever give names have you people, insignificant employees that you don't care about their identity, just a bunch of clones, you have to divide down by 1 over n factorial to compensate for the overcounting. And that makes stuff identical, essentially. Let us look at binomials and binomial expansion. Here is the binomial theorem in all its ugly abstract glory. So let there be 2 real numbers, a and b, and let there be 2 natural numbers, r and n. The sum of those 2 real numbers raised to the n power equals the sum of, from r to 0 to r equals n, the combination of these items being multiplied by each of these 2 real numbers in the binomial raised to these corresponding powers, a to the n minus r and b to the r. And this makes sense because, say, we have like n items here. We're again partitioning it into 2 groups of n minus r and r items from what we select out. So once again, n equals n, right? I can just arbitrarily add or subtract minus r plus r. That's what's so tricky about algebra. But then I can go and do parentheses here to conceptually group them into 2 distinct groups. And therefore that adds more conceptual meaning when you go and, like, say, tactical word problems. I have, say, like 10 pieces of fruit, and I want to distinguish them between oranges and apples. I therefore split them into 5 apples and 5 oranges. And you're just getting like these real numbers a and b here. You're multiplying them n minus r times. And this second real number b, I'm multiplying it r times instead to account for this partition that's happening in the exponents. So that's the binomial theorem here. And the binomial coefficients you get from the binomial expansion are identical to the combinations we spoke of earlier. It helps us to visualize these binomial coefficients. We can do so through a visual geometric aid called Pascal's triangle. Under the representation of Pascal's triangle, the variables r and n take on new meanings. So r in Pascal's triangle is the position, physical position, of the binomial coefficient, and n is the number of rows in Pascal's triangle. Now, what kind of sucks about this, so you have to start counting at r equals 0. But here's how we construct Pascal's triangle. We start with 1 here, and then across the left and the right diagonal, we always keep adding more and more 1s here, say for like here and here, so forth. But every time you go down from like the top to the bottom, 0th row to the 1st row, and then the 2nd row, etc., you take any 2 consecutive entries, add them up together, and they generate the number below that. So 1 plus 1 equals 2, you get 2 here, and then 1 over here and 1 over here. 1 plus 2 here, after I generate the 1 and the 1 here. 1 plus 2 here is 3, 2 plus 1 is 3. And I repeat the pattern here. 1 plus 3, 4, 3 plus 3, 6, 3 plus 1, 4, another 1, and I'm going to keep going. 1 plus 4, 5, 4 plus 6, 10, 6 plus 4, 10, 4 plus 1, 5, 1. And you get the general idea. Now, I mentioned or claimed that basically for the corresponding position of the binomial coefficient r and the row number n, if we pluck the appropriate numbers, we will get basically these combinations here in the formula. Now I have to be very careful. So I believe this 10, r equals 0, 1, 2, second position, so r equals 2. and 0, 1, 2, 3, 4, 5, fifth row, n equals 5. Let's check that C of 5 comma 2 does indeed give us 2, I hope. Okay, so then that's 5 factorial divided by 5 minus 2 factorial, 3 factorial. 5 factorial, 3 factorial, 3 factorial. And now we can use the recursive definition to split up the 5 factorial into 5 times 4 times 3 factorial. I can therefore cancel out the 3 factorial from there. I have a 3 factorial here. Oh, sorry. This gets canceled. This gets canceled. 5 times 4 is 20. Oh, wait. I'm sorry. Yeah, why does that write a 2? That should be, yeah, that should be a 2 factorial here. Okay. Good. Yep, 2 factorial. 20 divided by 2. That is indeed 10. And this generalizes in general. So you can check that, yes, it does give us the coefficients in there. What's kind of nice about Pascal's triangle is that there are numerous combinatorial patterns and formulas that you can find embedded within the sequence of numbers. Try and see if you can identify any of them. Now, there does exist a number array analogy for permutations, because I just said that like these combinations map to Pascal's triangle, but it's like, is there an equivalent visual aid for permutations? Well, there is, but that one is not used in the IBAAHL curriculum a lot because of its lack of any geometric symmetry. From that sentence, I think you should be able to easily deduce a key symmetry property already that Pascal's triangles and combinations have. Take a look over there and see if you can find out. If you want to relax the disjoint and independence assumptions of multiplication and addition principles, you need to embrace the natural number equivalence of Bayes' rule, at least though. And then also look at the generalized mutual inclusion-exclusion principle. Now, mutual inclusion-exclusion principle, what is that? That is simply assuming that we don't have disjoint sets. What does that mean? That means in the Venn diagram picture, which I will now draw now, say I have a universal set given by rectangle U. I have two circles in here, A and B. And I want to count the union of them now. A union B. That is just A plus B minus the intersection between them. Because remember, and I can't do this right now for sake of time, but if I were to color this area in one color, say like pink, and I were to color this in another color, say green, they would overlap in the intersection area over here and have two different colors. That's overcounting. We don't want that. So we have to go and subtract this intersection, or the cardinality of the intersection from here. This is basically the mutual inclusion-exclusion principle. And this is generalizable to 3 or more sets as well. Try and see what it is for like 3 sets. And then, well, good luck if you want to try for like 4 or n sets in general. Now, I would like to revisit permutations again. A permutation that picks n out of n items is n factorial. That is what we saw when looked at the extreme cases of we looked at one extreme case of the permutation formula we derive. I would like to note that we just considered this definition for finite sets. However, much to your possible pleasure or displeasure, this applies for infinite sets as well. Strictly speaking, in terms of functions or sequences, a permutation is just defined as a mapping of any set to itself. So a permutation in the abstract sense for infinite sets or finite sets. Let A be a set or event, and then let f of n be the function or sequence. Then f of n is mapping A to A for the domain to the codomain, and this is just like a permutation. Permutations are also bijective functions, which means there are injective one-to-one and surjective onto. Yeah, look up any possible future video I might develop on functions in general, where I go over these definitions. Alternatively, look at other math educator videos or articles that explain these concepts as well. The best short explanation I can give to unravel what a bijection is it is just a one-to-one correspondence between two sets elements. Now, another thing I want to go over. One combinatorial principle which I will state loosely and only just explain in terms of like set theory notation, not quantifiers, because I'm terrible at quantifiers and logical quantifiers are outside the scope of the course, is the pigeonhole principle. Imagine a coop or birdhouse that stores pigeons here. So I could say it's like a grid here, and I draw this following here. Let P be the set of pigeons, and then H be the number of holes. And say here we have P pigeons here, we have H holes here. And the function is defined, whatever it is. We have the domain as the pigeons, and it goes to the holes. We also know that we have more pigeons than holes. So P is greater than H. So the pigeonhole principle states if there are P pigeons and H holes that fulfill this condition, there must be a hole, must exist a hole with more than one pigeon. So say one hole here, there will be two birds. At least two birds, at least or equal to two birds. Now this principle is overkill for the main IB curriculum, but you may encounter it in the possible paper free, so I'm just listing it here. If there is demand, I will explain this in a possible future video with reference to problems on how to go and like solve things with it. Finally, I would like to go over some few guidelines that could help people new to combinatorics approach counting word problems. First, you could always solve counting problems directly or indirectly. In the direct case, you just use the multiplication and addition principle as you see fits, and the mutual inclusion-exclusion principle as well to go and solve the problem. But sometimes when counting certain items, you may either encounter the keywords at least, at most, not, or some conceptual indication of a negation. In that case, with the indirect problem-solving thing, you take the original thing you counted and subtract it by what you do not want to get your answer. So loosely stated, for this case at least, and of stuff you want, and that's it. That solves your problem. It's basically, there's no term for it because like complements only apply to probability, but this is basically the natural number version of it. Now the advantage of whether you solve a counting problem directly or indirectly is context dependent. So another second piece of advice I can give you on how to get better at combinatorics is to practice loads of questions. Thirdly, we can use pictures to distinguish different items visually from each other. There's traditional stars and bars mnemonic device used in mathematical teaching a lot, which you can look up for yourself, some videos of that. I will in the future post a video about using a new fictional character named Blob to assist you in solving certain counting problems. Again, to be continued in the future. And fourthly, if you have good intuition with size, check whether the largeness or smallness of the numbers is appropriate to the question. Finally, use extreme cases of the finite permutation and combination formulas I just derived and explained. That's it. That's all there is for this video on how to approach combinatorics in the IB analysis and approaches curriculum, particularly HL. To you IB candidates watching this video, I wish you good luck on your course.